Okay, I'm hoping we can finish topic 2 in this video. We're going to be looking at sampling and sampling distributions and the central limit theorem. So, when we are doing research, we can't test the whole population. It's just not possible with a large population. So it makes sense to take a sample. The more samples we take, the more effort it costs for the less return. So there's a sweet spot at which your sampling is pretty accurate, but not over strenuous. If you continue, you're going to get diminishing returns. Okay. Now, every sample we take is not going to be exactly the same as the population. A randomly taken sample, any value, any statistic, such as the value of the sample mean, will vary from sample to sample, okay? The sampling distribution of a statistic is the set of all possible samples of the statistic where all possible samples of a fixed size are taken from the population. And this helps us to predict how accurate a sample is going to be, what margin of error we can expect from that sample, okay, and how much variation we can expect in the data. And it's not that tough, don't worry. We're going to use our friend Excel to figure this out. So let's go over to Excel and have a look there right now. Here we go. Okay, say we take the temperature for 20 years in Saudi Arabia, okay? The maximum summer temperature for 20 years. From 2004 to 2023. And now we can kind of predict future temperatures from this. So we take all of our maximum temperatures here, temperature in degrees centigrade, and if we add them all up over 20 years and then divide that total by 20, okay, we're going to get a mean of 50.75. 50.175. Okay, so we take that mean and we pop it in here. All right. Then we take the individual data point for each year and we subtract that mean and we get a number here. Okay. And you can see that there's the coolest year in which there was the biggest difference, the average during that year of all the temperatures in summer. The highest temperature was 48, okay? And here we have the hottest year where the highest temperature was 51.6, okay? Then we square the difference between those two, all right? And if we take all those numbers and we sum them, and then we divide that square by n, we get the number called variance, 1.08. Variance of 1.08. 0, blah, 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 blah. Okay, now we take the square root of that, and we have our standard deviation. Our standard deviation is 1.039 degrees Celsius. Okay? That's one standard deviation from the mean overall. To get our standard error of how much we can expect, so now if we took the 2023 maximum temperature, we could expect it to be within 0.232 degrees of the mean, which is 50.175. So we could expect it to go up to 52.4 something, or as low as 47.9 something or 8 something, all right? And that we calculate by taking the standard deviation and putting it over the square root of n being 20 years, how many years we took that temperature that we've got samples for, okay? And if we were to draw it, here is a drawing that I made. Come on. Here is a drawing I made just to visualize it a little bit. So there's our average, it's 50.57 is our mean. The lines are hand-drawn, so they're not mathematically correct. There's one standard deviation within 1.08 degrees of the mean, okay? And our error is actually way over here. Can you see that? For the sample size, our error is way over here, which is quite interesting. So there's quite a big range of possible samples with a maximum annual temperature. All right. Okay. So back to the textbook. Again, Allison is a great tool for practicing. Oh, now I've lost the textbook. Hang on. Here we go. This is it. Oh. Trying here. Here we go. All right. So this is the textbook example. And I've just shown you all of that in Excel. So there's your sample units. There's your sample mean. You take that number minus that number, and you'd get a row of those totals. Then you square it, sum that, and then divide by n. And in this case, there's 10, n is 10, okay? Okay. So, the statistic computed from an individual sample is an element from the distribution of all possible samples, and this latter distribution is called the sampling distribution of the statistic. Okay, so normally we'll only calculate the mean from a single sample. All right. But we can still apply the basic principle that our sample mean will be a reliable estimate of our population mean and calculate the size of the error we would make if we use the sample mean as an estimate of the population mean. Note that the smaller the number of samples, the higher your standard error. This is specified in the central limit theorem, which we're going to look at now. The central limit theorem is as follows. If a simple random sample of size n is selected from a population with mean, and standard deviation, the sampling distribution of means obtained from all possible samples is approximately normal, with a mean average and standard deviation of sigma over the square root of n. If you've got one sample, the square root of n is going to be 1, okay? And your error rate is going to just be sigma. So, the central limit theorem gives a precise description of the distribution that you will obtain if you selected every possible sample, calculated every sample mean, and constructed the distribution of the sample mean. The importance of the theorem means that we can use it to describe a sampling distribution without having to actually sample a population of raw scores infinitely. So you can start to understand the big picture from a smaller slice, okay? It applies for any population, regardless of the shape of the Z curve, the mean or standard deviation of the original population. As n increases, the distribution of sample means becomes more normal. Okay? By the time n equals 30, the distribution is very close to perfectly normal. So we looked at in Excel an example with n equals 20. And was still quite a high level of error, I thought. Okay, so just as normal distribution is defined by its mean and standard deviation, so the distribution of sample means is described by the same two quantities, mean and standard deviation. The central value of the sampling distribution equals the population mean. So the mean of the distribution of all possible means is the same as the mean of the population. So if you have enough samples, your mean for the sampling mean is going to be exactly the same as it is for the whole actual true population. Okay. While the standard deviation of the sample means is estimated by a value we call the standard error of the mean. So like a standard deviation, the standard error of the mean tells us by what average amount the sample means deviate from the mean of the sampling distribution. So for example, if we go back to that Excel, it'll tell us that most of the temperatures of the hottest temperature of summer in Saudi are about 2 point something degrees away, 2.3 degrees off the norm. Okay, off the actual true average. And if we look at this, we'll see that there's one that's 2 point something off the norm, and we can expect more of them. Okay, I wonder if that's actually relates to the variance. I wonder what the average variance is. No, the variance average is that, sorry, 1.08. Okay. All right. Now, how we write the standard error is by saying sigma x bar. Sigma indicates we're describing the population, and the subscript x bar informs us that we're dealing with a population of sample means. So sigma x bar equals sigma over the square root of n. Okay, and here's a little drawing to explain it. Here's our actual population, and the average is 3. Here's a sample, and the average was 4. Here's another sample, the average was 3. Here's another sample, the average was 2. Here's another sample, the average was 1. Here's another sample, the average was 2. Here's another sample, the average was 3. Okay, as we have more samples, we can work out sigma x bar. Okay, and then we can see how accurate it is. So if n is 4, sigma x bar is sigma over the square root of n, so 10 samples, square root of 4, we can expect an error rate of about 5. If we have 25, sigma over x bar, 10 over, if our standard deviation is 10, then we can expect an error rate of 2. And if our sample size is 100, sigma x bar is sigma over the square root of n, 100. 10 over the square root of 100 is 1. We can expect an error range of 1, which is great, very accurate. Okay, so if the standard error is small, we know the sampling statistic is a relatively accurate reflection of the underlying population parameter. The larger the standard error, the greater the sampling error, and the greater the difference between the sampling statistic, i.e. the mean x bar, and the corresponding population parameter, which is mu, the mean, okay? Because of the central limit theorem, we now know something useful about the distribution of any mean, no matter how original data were distributed. Means tend to be distributed normally with a known mean and a known error when we try to estimate for a sample of reasonable size. So it's a formula that we can plug any sample into to see how it will correlate with the true population size. Okay, and give us a rough estimate of how off it's going to be. Okay, so we should now know how to calculate and interpret probability values. the law of large numbers, okay, which is like the more samples you have, the more close your samples are going to be to the true population. I think that's the law of large numbers. We'll have to look it up again. Additive and multiplicative probability rules for independent events. Remember that those are represented visually by the two interlocking circles. Okay. Additive meaning both circles, multiplicative meaning the area that they have in common. How to determine and interpret a conditional probability. Remember the tree diagram? How to interpret a probability distribution. How the binomial distribution represents probabilities for a discrete variable. Okay, tree diagram again. The standard normal distribution curve, that is the Z curve, as a probability distribution for continuous variables. So it's a Z curve in which the mean is 0 and the standard deviation is 1. Okay. How to determine and interpret a Z-score. The difference in samples and populations and the symbols used to describe them. The relevance of the central limit theorem to psychological research. How to determine and interpret the standard error of a sample mean. Okay, so law of large numbers, please go back and look that up for yourself. It's on page, it's right at the beginning of the topic. Okay, if you sit with me, I'll find it again. The law of large numbers. If an experiment is done repeatedly and if the outcomes are independent of one another, the observed proportion of favorable occurrences of an event will eventually approach its theoretical possible probability. Okay, so this is not actually about a curve, although it can be extrapolated to a bell curve. So in other words, if you run an experiment repeatedly, the more experiments you run, the closer your results are going to be to the classical theoretical probability that you calculate mathematically. So like a million coin tosses, you're going to find that your odds are extremely close, if not identical, to 0.5 throwing the heads. Okay, that's the law of large numbers. Okay, good luck. Let's leave it there. I hope this helps, and I'll see you in the next video in topic 3.